Here we are for another fascinating installment of Organic Chemistry in Sean's Basement. Today we're going to be talking about the prep of imines and enamines, not to be confused with amines. As we know, amines have nitrogens that are bonded to any number of carbons or hydrogens. And an imine is essentially either an aldehyde or a ketone version of something that has nitrogen in the place of an oxygen. So the first thing that is really nice is some of these names are actually fairly descriptive. So an enamine is specifically going to have a structure where you've got some sort of amine group directly attached to a carbon that itself has a double bond. And then of course you have whatever else you want connected out here. So the way that we're going to produce these enamines, right, is going to be with secondary amines attacking some sort of aldehyde or ketone, right? Keep in mind that's one of the things that it kind of unites this whole crazy chapter is we're always doing carbonyl additions to aldehydes and ketones. An imine is very, very similar. The imine, as I said, is really the nitrogen equivalent of a carbonyl group. And you'll notice that the structure allows us to actually have an additional R group on here. And so these things, called an imine, are going to come from primary amines as they react with some sort of carbonyl on a ketone or an aldehyde. Now, another thing that kind of unites much of this chapter is that anytime we produce some sort of addition product like are shown here, one thing that's going to often be the case is that we can reverse this with the addition of H2O, right? And so if you think back to the Le Chatelier days of lore, when you were doing general chemistry and you saw, for instance, that you remove a product, right? And so in this particular case, after we attack either a ketone or an aldehyde, and we produce one of these structures, you'll see that water is a side product. If we kind of suck water out of that thing with something like a molecular sieve, or there's all kinds of different ways to drive off water in a reaction that we would talk about if we were actually in lab, either with a Dean Stark apparatus or something like that. The way to get these things to go back to their aldehyde and ketone parents is to actually add water. And of course, these things usually require some sort of very, very slight acid catalysis. So let's take a look at the mechanisms for both of these. And you'll notice that they're very similar with one little tiny change at the end. So, as we know, these nitrogen species are very good nucleophiles. So we're going to be able to directly attack that carbon regardless of whether or not we have the presence of any kind of catalytic acid around. Sometimes it's a little bit easier to use a little bit of acid to get this process started, but you do have a little problem where if you do have catalytic acid, it's probably going to protonate some of those nitrogen species, and you might actually it might be counterproductive, right? And so when I did these reactions, I just like to heat the bejesus out of them and to not worry about any kind of acid. So, as we know, if we have a strong enough nucleophile, we're going to be able to directly attack the carbon of the carbonyl, and we've got our normal flow of arrows. Now, as I draw this intermediate, this is kind of an odd situation that we have yet to encounter. And you're going to probably notice that I'm going to have both a minus and a positive charge in my mechanism. And usually this is the sign that you've done something wrong, but nitrogen has some special chemistry. And so it's actually okay to show something like this. It's actually what's called a Zwitter ion. And so that's a really common thing that you're going to see in a lot of different nitrogen mechanisms. As I said, if we did have catalytic acid around and we protonated that, then we would avoid that minus charge. But it's not a very big deal. And so just like we've seen in several other mechanisms, I'm going to use another part of this reagent to simply move the H from one place to the other. So if I take just a second to point something out here, what you'll notice that we have here is kind of the nitrogen equivalent or the amine equivalent of a hemiacetal. And so just like we saw with the other mechanism where we formed acetals and ketals, the very next step to get to kind of the full-blown version is going to have me protonate this and then show that particular group leaving. Since there's no acid around, what I'm going to do is another kind of unusual thing for a nitrogen mechanism. So at this point, I'm going to show this lone pair of electrons coming down and eliminating a hydroxy group. Once again, that's not the best leaving group. I feel okay with it because this reaction, keep in mind, when I usually did these reactions, I'd heat them up quite a bit, and so kind of some odd, unusual things can happen, and it'll actually get us pretty close to the final product here. The only difference is that there'll be a hydrogen on the imine that we have to deal with. And in the very next step of the mechanism, all I do is I show the hydroxide coming in and ripping off the proton, and then we have the production of our true imine. One thing I did want to mention about this is that a lot of pretty exciting syntheses can occur from something that looks like this. There's also some biological mechanisms that have this kind of moiety as an important part. Oftentimes you'll hear about something like a Schiff base or something like that when you get into some more advanced biochem. Another fun thing about these is that if we had something a little bit more exciting than ethyl group and we wanted to do some more exciting chemistry or more synthetic type reactions that have a little bit more excitement, you can actually put some sort of chiral carbon in here. And in a sense, what you've done is you've curated a chiral compound that you can, because it is chiral, treat with some other kind of chiral reagent and get some really nice enantioselective properties out of some reactions. So this is a good one to know. And now we'll move on to show you how the enamine mechanism is very, very similar, except for the very end. And of course, you'll notice here we're making an enamine. So I showed just kind of a random secondary amine. And you'll notice that the mechanism is very, very similar. So now that we've gotten to this point in the mechanism, one of the things you'll notice is that I no longer have that hydrogen that I can have ripped off to get to a neutrally charged intermediate. So what is going to happen is a little bit of a preview of things that are going to come in third term that has to do with that alpha carbon chemistry. So the way that we're going to get that double bond, the carbon-carbon double bond I should say, is that now instead of extracting an H from here, we're going to extract an H from the alpha carbon. And you'll notice that what we end up with as a result is our final product, the enamine. And once again, I show it now, but in third term, we'll also learn about some kind of exciting alpha carbon chemistry and substitutions that we can do that otherwise wouldn't be available to us using this thing. In fact, there's a man by the name of Stork that came up with a whole series of synthetic protocols involving these things. So we will see all of these things again next term.